Hello, welcome to Localization System project presentation. This project was made by myself, Mohammed Al-Jashi, Michael Nazarov, and Joel Sandoval under the advising of Dr. Kim. There are a lot of ways that people use to track a missing item. One of the methods that have been used is the conventional method. This method requires a reference record point where record the last known location for the item that trying to track. So the problem we're facing is a lot of things is missing every day and people has no idea where are it. And the convention method that has a problem that does not track in real time. So to solve this problem, we're gonna use RF beacon. This beacon is gonna attach to the item that we need to track, and it's gonna transmit a signal to the receiver where we're going to use the direction of arrival method to calculate the distance and the location of the missing item. One of the reasons we're going to use the RF beacon because it allows us to track one single item at a time. This picture shows our design. Our design contains a transmitter where it's going to be attached to the item that we need to locate, and it's going to send the signal to the receiver. Our receiver contains of two antennas where they're going to collect the signal from the transmitter and send it to local oscillator. The local oscillator is going to send it to low pass filter to filter the signal and then send it to amplifier. The amplifier is going to send it to the DAQ where it's going to convert the signal from analog to digital. And the reason we're using the amplifier here before the DAQ because the amplifier itself has a noise signal. So to get rid of the noise we're using the amplifier. And after the conversion, the digital signal is going to go to the computer, collected by the LabVIEW, and then the LabVIEW going to send the data to the MATLAB to do some calculation to find the location of the item. Now, Joel Sandoval is going to talk about the hardware and how it's work.
My name is Joel Sandoval, and I'll be talking to you about the actual hardware of this project. Here we're dealing with an RF system which is mainly composed of two things, the transmitter and the receiver. On the transmitter side we have a 433 MHz RF transmitter which sends the RF signal continuously. On the receiver side, at the front end we have a two antenna array which is connected directly to two mixers. A mixer is a two input one output device. At one of the inputs we have the antenna which picks up the signal coming from the transmitter. At the other input we have the VCO signal. As the name suggests, it's a voltage control oscillator, which means that we have to set up or apply a certain voltage to the VCO in order to make it produce a certain frequency. So the first thing we do is to set up or apply the tuning voltage to the VCO in order to get a frequency really close to the carrier signal or the signal from the transmitter. The output of the mixer is then connected or sent through a low pass filter, and this is in order to reject all the high frequencies. The output of the mixer is sent through an amplifier in order to amplify the signal, which will make it easier for sampling later on the process. At the back end of that receiver we have the DAQ, which is a digital acquisition device, and at this device we have connected two inputs, which are the inputs from the amplifier, and this device is gonna sample the analog signal from the amplifiers in order to transmit it to a computer. The DAQ will sample the signal and will dump it into MATLAB, which that information will later be used in order to calculate the angle of arrival. This is the actual program that comes with the DAQ. As you can see, this displays the actual or real-time signal and the spectrum domain of the signal. More information about this will later be given by Michael, which will be presenting next.
Hi, I'm Michael Nazaroff. I'll be discussing the sampling and a digital signal processing part of this video. Before we do the DSP, we first sample the data using National Instrument Signal Express using a DAQ or data acquisition device. As you can see, the layout here is how we could choose the inputs. Right here you can see how we have analog in 0 or analog in 1, which pretty much says channel 0 and channel 1 of the DAQ. Right here we have a sampling rate of 24 and we have 1024 samples. The sampling rate was chosen because the maximum sampling rate of the DAQ is at 48 kilohertz, but when you have two channels it's pretty much split in half to share amongst the two channels. And also if you have 4 channels sampling at once, it'll be 48 divided by 4 or 12 kilohertz maximum sampling rate. So right here, this was pretty much a bottleneck, well, one bottleneck of our design, as we had to be able to down convert our received signal at least below the Nyquist sampling rate of 12 kilohertz. We pretty much shot for between 2 or 6 kilohertz because we didn't have a phase lock loop, so we had to fine tune the VCO. Also, right here we save the signals, as you can see here. It's saved in a voltage.txt file, which can be opened in MATLAB, and which is how we're going to be processing the data. It saves it in 3 columns. The first column, it uses relative time of the sampling. Second column is the sampling right here from analog in 0, and the third column is from the other channel, channel 1. Now, after we have the sample data, we use MATLAB to analyze the spectrum of the signals that we had. Our proposed method actually was a fast Fourier transform, or FFT. Before we had the hardware implemented and built, we used MATLAB scripts to simulate what we should expect for our signals. The script consisted of doing a simulated sample signal of a particular frequency, then perform FFT on this signal and viewing on the spectrum and viewing where the peaks of our signal occurs on the FFT spectrum. This actually led to inaccuracies using the FFT, one of which was the frequency of the signal appearing at a different frequency than it actually was. For example, if we had a frequency of, say, 1.04 kilohertz, the FFT would show the signal showing at 1.10 kilohertz, or probably 9.99 kilohertz. This is actually caused by what's called leakage, which is when the frequencies of the signal does not fit correctly into the discrete bins of the FFT spectrum, which causes it to spread or leak into other bins and causing the frequency to appear at different frequencies than it actually is.